Back to another video, guys. You're on the pick of the week, that specific selection for interesting and sometimes complicated problems. We're going to clarify all necessary steps in order to solve that. Sorry guys for long absence. I've been doing my dance video clips. Sorry for that. For those who are interested in dancing, how to dance, and basically just want to watch my dance videos, just welcome to my channel, Daniel Dallas, How to Dance. You can also find this link in description. Alright, so that's tutorials, video tutorials from the very basics up to more advanced techniques. And this is from hip hop, breaking, and up to animation style. Alright, let's get back to math and let's have a look at mathematical induction as primary topic for A-level, IB, HL level, and also probably standard level if you're interested in more advanced math. And today we're gonna go through several examples where you clearly see how to use mathematical induction in order to prove. But before, I'll just try to mention all necessary steps in order to apply mathematical induction. So basically, I'll tell you the essence of math induction, what it is. Okay, so let's go to the essence of mathematical induction. Basically, the main steps that you need to clearly show in order to prove your statement, your formula, whatever you're given. All right, so let's go to the principle of mathematical induction. We have the statement or rule about some positive integer n. So n should be positive integer. So it might be any formula, for example, the sum of arithmetic sequence, a1 plus a2 plus an finally is n times a1 an over 2. So everywhere you can figure out or you can see number n. So that statement you need to prove. So what do you need to do? You need to prove that for a specific base number, for example, it might be any number, but normally people and students use to put n equals 1, the minimum base statement, unless you have specific limitations or limits and restrictions for n. So in this case, n is going to be just simple positive number, and we're trying to take any simple number so that you can check your formula that it works. All right, so that means in case a1 we have n equals 1, we have just one single term left in the left side. What about the right side? We just simply plug into the formula n equals 1, and we've got a1 plus another a1 over 2, and we've got a1 as well. So this statement is true, all right? So base statement is completed and proved. Second step, you need to make assumptions. So we assume that statement is true. So the statement is true for n equals specific number k, no matter which k you take. So, but obviously it's going to be positive integer due to the fact that n more than 0. All right, so we assume that the statement, the formula is true for n equals k, and we need to prove now. Now what you need to do is to prove, try to prove that the statement is true also for n equals k plus 1. So once you've done that, once you are able to prove the statement is true also for n equals k plus 1, basically for the next n number, right? So next number in the sequence is going to be k plus 1. So if you've done that, the result or outcome is that your statement will be true. So your statement will be true for all positive numbers. Okay, numbers. So that means it will be also true. It will be also true for any positive integer. Positive integer. All right. And let's have a look at 3 problems that we're going to go through in order to solidify your theoretical basis about mass induction. Here's the first problem, here's the second one, and here's the third one. Try to pause the video, try to do by your own as always, and let's get started. So I just remind you that set of problems, it's definitely IB style, H level, IBHL style, exam styles questions, and also you can find similar in A level program. So that's basically the main their focus auditory of students who are eligible to do and who needs to be able to do this sort of questions. For all others, you are also welcome, guys. Try to understand the general principles of math inductions. All right, so let's get started. So here you're given n plus 1 term. I'm not satisfied with that one, so I can also rewrite in the way un equals 2 to the 2 times 3 to the power n minus 1. So I can just use it for any number k because that's what we are given as a true statement. So we need to use principle in order to prove that the left-hand side is equal to shortcut 3 to the power n minus 1. All right, so that's our target. All right, so let's apply the principle of math induction. We need to first prove for a specific number n, and that's going to be our base statement. So let's plug n equals 1. So you're eligible to plug actually any number which is more than 0 because we understand that the sequence starts from u1 term, and the u first term is going to be the very first term in the sequence. So number n starts from 1 and run to up to infinity. So that's why you can also plug any number you like as the base statement. So you can plug n equals 2, n equals 3, but I would like to not to be to make our calculations overcomplicated. So that's better to use as simple as possible. So that's why I plug n equals 1. And let's check this formula, whether it's correct or not. So in this case, we stay with only the very first term, u1. And on the right side, if we plug n equals 1, we'll get 3 to the power 1 minus 1, which is 2. So we've got the right hand side of the equation to be equals 2. And now we need to use general formula for nth term when n equals 1. Right now, we just need to figure out what u1's your first term, and this sequence is going to be equal to. All right, just everywhere we plug n equals 1, and we've got 2 times 3 to the power 0, which is 2. So we figure out that u first term is 2, the right side is also 2, so that means it's correct, and the formula works for n equals 1. So the base statement is true. Now let's prove that this formula also works for n equals k plus 1. So we need to prove that formula works for n equals k plus 1 if the statement, if the formula is correct for n equals k. So that's our assumption. So we assume that. So, and we say that the formula works for n equals k. So we need to prove that it also works for k plus 1. So if it's correct for n equals k, we just simply can rewrite this formula as, let's write here, u1 plus u2. Whenever n number stays, we just plug k number instead. So that means finally we've got uk, and the right side will look like 3 to the power k minus 1. Okay, so right now what we're going to do, we need to prove that this formula also works for n equals k plus 1. So we just need to plug and see how the target formula, how the right side of this equation will look like. So we plug k plus 1 instead of n, so that means we've got u1 plus u2 plus, and finally we've got plus. Before writing just k plus 1 term, I'll write pre-last term as uk, and finally the last term uk plus 1. As our target, you simply understand that if you plug n equals k plus 1, we need to be able to prove that right side should look like k plus 1, 3 to the power k plus 1 minus 1. So this is the target, and that's what we are supposed to prove. So this is the target. All right, so you clearly see that we've got the sum of the first k terms. So that's going to be the sum of k terms, first k terms, in our sequence. But we already have this, right? So this part will give us, according to the formula, because assumption is correct for n equals k, 3 to the power k minus 1. And also we've got another one. On top of that, we need to add k plus 1 term. Here, we can simply use the formula for k plus 1 term, that in this case will give us 2 times, instead of n, we just use k, because we use k plus 1 term, so that means in general we've got 2 times 3 to the power k. And if we add this, we should arrive to our target, so this is the target. Okay, so now let's simplify that. 3k to the power k and 2 times 3 to the power k will give us 3 times 3 to the power k and minus 1. But using the property of indices, so we can say that this part is going to be simply 3 to the power k plus 1 and minus 1. So we've got our target state, our target formula. So that was on the left side. Okay, so that's what we've got on the left side, and that will be equivalent to the right side, our target. So we've got the target statement, and that means if the formula correct for n, some random number equals k plus 1, it will be also correct for any positive number. So that means as outcome, this formula works for any number n, for any positive number n. So that means we proved that. Okay, so we proved. Let's move to the next problem. So here's the same. We need to use principle of math induction and show that. In this case, I'll just start speculating faster, a bit more faster. Okay, so let's check for n equals 1. We simply will get 1 squared, because we'll stay with n equals 1, just one single term. And on the right side, let's calculate 1 over 6 times 1 times n plus 1, 1 plus 1, and 2 plus 1. So 3, 2 is going to be 6 over 6, so that's going to be 6 over 6. So that means we've got also 1, because 1 squared, so 1 equals 1. That means the base assumption is true. So, sorry, the base statement is true, for it works for n equals 1. Now we need to make an assumption, so assume this formula works, so it works for n equals k. So we need to prove that, so prove that it also works for n equals k plus 1. All right, so how to do that? Just again, let's set up the first key terms in that series. 1 squared, 2 squared, and up to k squared. And on top of that, we just need to add k plus 1 squared. So this part is definitely, because this formula works for n equals k, so that means the formula will look like 1 squared plus 2 squared plus, and the rest part is going to be, the last term is k squared. So we just simply rewrite this formula by plugging n equals k. So that means we've got 1 over 6, k plus 1, and on top of that we need to times 2k plus 1. Okay, so that formula is true, and that means our target. Now let's write the right side. So if we plug instead of n, whatever n stays, k plus 1, we should get the target formula that we need to approach to. So everywhere we plug k plus 1, k plus 1. So here k plus 1 and plus 1 is going to be k plus 2. And finally 2n plus 1 is going to be 2k plus 2 and plus 1 is going to be plus 3. So we need to prove that this whole stuff is going to be that. So that's our target. So I just put the words. This is what we need to arrive to. So that's our target formula. Okay, so let's try to do and just squeeze a little bit. Okay, and let's try to speculate. So we've got the first part and we've got the second part. So the first part, we just simply plug the formula. We can use that 1 over 6 k plus 1 and 2k plus 1. And on top of that, we need to add k plus 1 term. So that means just simply eligible to use the same denominator, and I'll use that one. All right, now we need to simplify. So let's simplify. Let's just come to common denominator, or just factorize 1 over 6 times k plus 1 is also possible, can be possible factorize. So k plus 1 here, and in the brackets, what's left? We're left with k times 2k plus 1, 2k plus 1, and plus 6k plus 6. All right, because k plus 1 left here, and we just simply expand the brackets. All right, so let's simplify that first of all, and we've got k plus 1 over 6. Okay, it's here. Then k times 2k plus 1. Okay, so we've got k times 2k plus 1. Let's factorize. Let's expand the brackets, and we've got 2k squared plus, it's going to be k, and 6k is 7k. And on top of that, we've got 6. So we've got 6 as a free coefficient. Now, our target looks like we've got this part. It's right there. So it's right there. But we need to factorize 2k squared plus 7k plus 6. If you're not sure, if you want to have a little shortcut, just try to expand these brackets and just try to show that you'll get this. All right, so that's what I'm going to use. From target formula, just simply expand the brackets instead of factorize, because factorize is always harder. So I will use 2k squared, then k times 3 is 3k, and 2 times 2 is 4k, 7k, and 2 times 3 is going to be 6. Yeah, so that works. That means this expression can be factorized in this form. So that means from here, we've got our complete statement, our target statement, which is 1 over 6, k plus 1, k plus 2, and on top of that, we'll get 2k plus 3. So we've got our target, because left-hand side, we're starting from here, and we arrived to what we have on the target on the right side. So we proved that. That means outcome, again, that works for any n positive integer. All right, let's move next. All right, so in this case, you need to prove that n plus 1 plus n plus 2 and so on up to 2n equals to 1 over 2n times 3n plus 1. So you're not clearly stated by which method you need to prove. So you can try to use mathematical induction. However, I think it will be much longer. So that's why I'll offer you an alternative method. Definitely shortcut. Will be based on arithmetic sequence, and that's going to be a hint for you guys. Try to maybe pause the video and try to do by around using that hint. If you've done using mathematical induction, that's how you can practice and work out using several alternative methods. Okay, and if you've done using mathematical induction, just share in comments was it successful or not. If not, I'll just clarify this method in the next video, how to prove that using math induction. Right now I'm going to use an alternative method. I've noticed that n plus 1, n plus 2, n plus 3, they're terms of arithmetic sequence. So I can definitely say that the very first term is going to be just simply equals to n plus 1. So that's the very first term. How many terms in total? So I'm just wondering about the last term, which is 2n. So that's going to be the last term. But what's the number stays here? All right, so let's calculate. Just simply we need to, because we know this is the series of arithmetic terms, we just simply can use the fact that from 2n, the last term, we can subtract the very first term, n plus 1. And that's how we basically count how many terms on the row, yes? And on top of that, we just need to add 1 because simply we need to take into account the boundary term, okay? So that means in that case, we'll get n minus 1 plus 1, so n terms in a row. So that means from here to here, we will have n terms of arithmetic sequence. So that means un's term is going to be 2n. Okay, so just remember the formula for the sum of the first n term, from the first to the nth term in arithmetic sequence. Is simply u1 plus the last term un over 2 times the number of terms, in this case n terms. Alright, so just let's try to apply this formula, because the result, that's going to be the target that we need to get finally. That means the sum of the first nth term is going to be equal, we just plug, instead of u1 n plus 1, instead of un we plug 2n, the last term, we divide by 2 times n. So that means we've got the sum equals 3n plus 1 over 2 times n. And indeed, we've got this formula. You just have a look at the right side of the formula. It works. Okay, that was pretty short. Trust me, using math induction is going to be much harder, and definitely it takes more time from you, much more time from you. So that's why I like this method. It's going to be, of course, it's based on well-known formula, so you need to mention that we're using well-known formula, and that's how we can prove. Hope you liked the series. That was all about math induction. Please like, please subscribe, and see you next time. And one more time, sorry for the long absence. I was busy with my dance video. Don't forget to check this channel as well. See the link in the description below. That was Daniel Dallas. Peace out.